Imagine holding the world's most advanced mechanical calculator in the palm of your hand, a device that revolutionized computation long before the digital age. This is the Curta calculator, a marvel of engineering and ingenuity. Designed by Kurt Hertzstark in the 1940s, this pocket-sized powerhouse became a trusted tool for engineers, scientists, and mathematicians. From its inception during World War II to its peak popularity in the mid-20th century, the Curta calculator was renowned for its precision, durability, and portability. Unlike today's digital calculators, the Curta operates purely on mechanical principles. No batteries, no electricity, just the intricate dance of gears and levers transforming human input into accurate calculations. In this video, we're going to dive deep into the mechanics of the Curta calculator. We'll explore how it works, why it was so revolutionary, and what makes it a collector's dream today. This is a Curta Type 1, and it comes with a sturdy metal container. Before we dive into its internal mechanisms, let's first learn how to use this remarkable device. Around the outside of the cylindrical Curta, you'll find the input sliders. These sliders click into place at each whole digit, with a wheel above each slider showing the entered digit. There are 8 input sliders, allowing you to perform calculations with numbers up to 999999999. At the top of the Curta, you'll notice 2 sections of numbers. The black section, consisting of 11 digits, serves as the accumulator, where the results are displayed. This means the results can be up to 1,000 times larger than the largest input. The white section, with 6 digits, is the counter that tracks the number of turns you make with the crank. To operate the Curta, you turn the crank at the top a full 360 degrees. The white section shows the number of crank turns. The crank operates in 2 modes and can only be turned clockwise. In its default position, each turn of the crank adds the inputs to the outputs. To perform subtraction, you need to pull the crank up slightly, and each turn will then subtract the inputs from the outputs. There is also a clearing lever at the top to reset all the registers after a full rotation. Under the clearing lever, there are 5 decimal markers that can be moved freely and are used to mark the decimal position or used as thousand separators. There are also 3 decimal markers located under the input sliders for inputting decimal numbers or use as thousand separators. Let's try adding 345 and 678. First, set the sliders to 3, 4, and 5. Then, rotate the crank a full turn. This will add 345 to the result registers, and the counter register will increase by 1. Next, set the sliders to 6, 7, and 8, and rotate the crank again. The total sum of 1023 will appear in the result registers, and the counter register will increase by 1. Each rotation of the crank adds the input's value to the result and increments the counter by 1. This principle allows for multiplication through successive addition. For example, to multiply 135 by 18, first set the input sliders to 1, 3, and 5. Rotate the crank once to add 135 to the result register. Continue rotating the crank until the counter register reaches 18. For larger multiplications, such as 1290 by 873, it's impractical to rotate the crank 873 times. Instead, the entire carriage is moved to different positions, corresponding to powers of 10. In the default position, each crank rotation adds the input register values to the result register. In the second position, each crank rotation multiplies the input by 10. In the third position, by 100. In the fourth position, by 1000, and so on. To multiply 1290 by 873, set the input registers to 1, 2, 9, and 0. Move the carriage to the third position and rotate the crank 8 times, adding 1290 times 800. Move the carriage to the second position and rotate the crank 7 times, adding 1290 times 70. Move the carriage to the first position and rotate the crank 3 times, adding 1290 times 3. The result, 11,206,172, is the product of 1290 multiplied by 873. Division is achieved through successive subtraction. Although the Curta is primarily designed for addition and subtraction, various algorithms and techniques allow it to perform functions like finding square roots, sine, cosine, powers, and more, though these are beyond the scope of this video. There's also a small switch on the side of the cylinder that determines whether the counter register increases or decreases after each crank rotation. By default, addition increases the counter and subtraction decreases it, but this switch can override that behavior. Now that we understand the basic operation, let's explore the incredible internal mechanisms that make the Curta a true mechanical marvel. The Curta calculator consists of many intricate parts working together. To make it easier to understand, we'll break it down into simple, easy-to-understand mechanisms. First, let's understand how addition and subtraction can be achieved mechanically using gears. Imagine 2 gears of the same size. When one gear makes a full rotation, the other gear also completes a full rotation. Let's label the first gear with numbers from 0 to 9. Each full rotation of this gear represents adding 10. To add just 1, we can rotate the second gear by a tiny amount. Alternatively, we could equip the second gear with only 1 tooth, so each rotation adds 1. This concept can be extended. A gear with 2 teeth adds 2, a gear with 3 teeth adds 3, and so on, up to a gear with 9 teeth adding 9. By making the first gear slide along its shaft using a groove, the shaft can rotate with the gear. Shifting the first gear to the desired number allows us to add that number by rotating the second gear's shaft. This arrangement, called a step drum or step cylinder, forms the basic principle of mechanical addition. Now, let's return to our Curta calculator. For better readability, I will use color shading for the internal mechanisms instead of realistic shading. The main frame of the Curta consists of 2 aluminum castings connected by 3 copper columns. At the top of the upper main casting is a carriage body that holds all the result gears and counter gears. The setting shafts are located between the 2 main castings and are supported by small bearings at the bottom. Behind the setting shafts are the transmission shafts. When you move the input slider, the digit changes accordingly, and the slider snaps from one digit to the next, ensuring accurate digit input. The slider knob moves over a shaft with a spiral groove. On the other side of the knob, a rod slides along the groove, converting the vertical motion into rotary motion. At the top of the shaft, a number wheel is attached and rotates with the shaft. To ensure precise digit snapping, a spring-loaded ball rides along the groove, catching on spherical pits at each digit position. Behind the slider is a transmission shaft. Moving the slider also moves a count gear along the transmission shaft. Since the count gear is fitted into the groove of the shaft, it also rotates with the transmission shaft. At the end of the shaft, a bevel gear transfers the rotation to the number wheel of the accumulator. All the other number wheels are also driven by the transmission shafts. With this arrangement, we can easily see how many steps the count gear turns. The main part of the Curta calculator is the step drum, also known as the Leibniz wheel, named after its inventor, Gottfried Leibniz, and it is connected to the main shaft. When you rotate the crank, the step drum connected to it rotates and engages with the transmission gear. The teeth on the step drum align with the input sliders. For instance, when set to 1, the transmission gear meshes with the section of the drum with 1 tooth. Set to 5, it meshes with the section with 5 teeth, and so on. The step drum has rows of teeth ranging from 0 to 9. Rotating the crank moves the step drum through each transmission gear, transmitting the input numbers to the result registers. For instance, set the input to 6. This aligns the transmission gear with the 6-teeth section of the step drum. Rotate the crank, and the step drum drives the gear to rotate 6 steps, setting the result register to 6. To add 3, move the input slider to 3. This aligns the gear with the 3-teeth section. Rotate the crank again, and the gear rotates 3 steps, resulting in a total of 9 in the result registers. When adding larger numbers, we need to manage carries to the next transmission shaft. For this, another gear is added to the transmission shaft along with a carry sensing lever which can slide up or down in its housing. A small clip spring ensures it stays in the required position. Each number wheel of the result register has a small pin that, when passing the number 9, pushes down the carry sensing lever. This action moves the carry gear on the next transmission shaft to a lower position. To mesh with this carry gear, a cam with a single tooth, called the tens bell, is added to the crank. When the crank is rotated and the carry gear is in the lower position, the tens bell advances the gear by 1 step, ensuring a successful carry. The tens bell also includes a carry reset ring to reset the carry levers to the up position after adding 1 step to the carry gear. Let's test this by adding 2 numbers, 6 and 8. First, set the result register to 6 by moving the input slider to 6 and rotating the crank. Then, move the slider to 8 and rotate the crank again. When the result gear passes 9, the carry pin pushes down the carry sensing lever, which also pushes down the carry gear on the next transmission shaft. This gear then aligns with the single tooth of the tens bell and is driven by 1 step. As a result, a carry is successfully sent to the next digit, giving us the correct answer of 14. By using this carry mechanism on all transmission shafts, we can accurately add any numbers we want. In part 2 of this video, we will explore how subtraction is implemented, how the counter works, and how the carriage position enables the Curta to multiply large numbers, among many other fascinating details. If you enjoyed this video, please like and subscribe to stay tuned for part 2. See you soon.